Okay, so I'm going to talk today about fast interrupts. This is a new task group that we just created. I'm sharing this with Kevin Chen from Andes as the vice chair. So this is part of, I mentioned in the talk, the first talk, we have an emphasis on embedded. We'd like to push on that this year. And obviously embedded is one of the major use cases for RISC-V. One thing I'll say up front, because everybody has a different view of what embedded means, it does cover a very large swath, much larger than Unix space. You have everything from tiny microcontrollers with a kilobyte of memory up to large multi-cores with lots of scratch-pad memories working really fast on fast I/O. So there's many different kinds of embedded system. There was a general sense that a lot of the members wanted to have some faster scheme. They were seeing problems, with the existing scheme. I'll go over those. The desire to work on a faster interrupt scheme, and particularly to have support for nested, preempted interrupts. So in the current scheme, while you're running a handler, typically the interrupts are disabled. You have to wait till it finishes before you can take the next interrupt. And so handling nested interrupts is one of the main goals. So task group started XXX. I didn't put the date in. It started recently, the last few months. It's the early days. This is really more giving you the idea of what the problem statement is and how we've started thinking about this. And if you're interested, please join. The members just go to the workspace and join the fast interrupts working group. Okay, so I thought I'd start off with going over the current RISC-V interrupt scheme, so people would get, just to get everybody up to speed. So there's two kinds of interrupts. There's local interrupts. These are directly connected to one of the hardware threads. One of the hearts has an interrupt. The nice thing about these is there's no concept of arbitration. The interrupt is for this particular heart. It's going to take the interrupt if it's presented. And you can directly look at which interrupt it was by looking at a value in the cause register. And in the base standard thing, there was only two standard local interrupts defined, which was the software interrupt and the timer interrupt. In addition, what we added after a while was the idea of a global interrupt controller. We have this very simple thing we call the PLIC, the platform level interrupt controller. And the idea of this is where you have interrupts that you need to route between multiple cores, multiple hearts, where you'd like to have some priority. You have this external controller that handles that, and that presents a very simple interface to the core, where there's a single interrupt line coming in, and there are a bunch of memory mapped registers you read and write to figure out which interrupt it was, to claim the interrupt, and then to signal that you've completed with a handler. So this PLIC we added, initially we didn't have an interrupt controller. We felt that was part of the platform specification. But in order to start getting Linux up, we had to define something, and the PLIC is what we defined at that point in time as the platform level controller. So kind of an overview of the way the interrupts work. We have this, I think this is a laser pointer somehow. Oh no, this is a laser pointer. Specialization, see. You have the global PLIC, which takes platform level external interrupts. Then inside here, you can route these to different threads. And inside here, there's the circuitry does the prioritization of those interrupt sources for the different threads. Now, one thing to notice, each of the hardware threads has a stack of privilege levels. Just realized I forgot to remove H. Just ignore the H. So you have user, supervisor, machine mode on these hearts. And each of those gets a separate input from the PLIC that can interrupt that given privilege mode if it's running independently. In addition, there is separate timer and software coming in each privilege mode on each heart. So these are the local interrupts. Those are dedicated for each heart. And these are the global interrupts that are routed to those hearts. All right, so that's the overall scheme in the current RISC-V interrupt land. So the way this appears inside the machine at the ISA level, there is a machine interrupt pending register, the MIP CSR. And in the low bits of this, you have the various local interrupts showing up. So one way to think about MIP, it really is just local interrupts. And the external interrupts just all come down into a single line that comes in as the external interrupt. Right? But you have the separate bits for the software interrupt, timer interrupt, external input from the PLIC. And in the upper bits of this word, we said bit 16 and up are reserved for custom local interrupts. You can just wire things in there directly to get very fast local interrupt handling. So this is a local interrupt scheme. but then go to the MIE bit, which is the machine interrupt enable. So MIP tells you which interrupts are there. You can view those as the wires coming from those devices. Then the MIE is how you can selectively enable or disable each of those different sources of interrupts. So it's just laid out in a parallel format. It has an enable bit for each of those interrupt sources, and you would extend that up for the custom interrupt sources as well. That just gives you the per interrupt enables. So when you take an interrupt, let's go look at mstatus. So in mstatus, there are global interrupt enables. So these are really the sort of master switch on interrupt enables for a given privilege mode. So if you have mstatus.mie clear, then you won't take any interrupts in machine mode, right? It has to be enabled if you take any of those interrupts in machine mode. Similarly for supervisor user mode. Now, when you take an interrupt, you have to remember where you came from to be able to restore the context when you go back. And so we have an enable stack and a privilege stack that remembers the previous interrupt enable state and the previous privilege mode state. And those get restored when you execute an mret. So I'll talk a bit more about that later. But those bits are currently in the mstatus register, wired in there. So when you do take an interrupt, the interrupt report is reported which one it was as a field in the cause register. And the way we laid out the cause register was that the high bit distinguished between an interrupt or a synchronous exception. And so the high bit tells you that if it's set, that there was some kind of asynchronous interrupt coming in. In that case, the low part, the exception code field, tells you which of the interrupts it was. And the value there is just which of the bits in MIP caused that interrupt. Now, if this tells you that the interrupt cause was the PLIC, an external interrupt, you then have to go to the PLIC to find out which of the inputs to the PLIC caused that, the external interrupt to be raised. And so there's some extra memory operation you have to do there to go find out the actual interrupt cause. So what happens on an interrupt? Well, the cause is set, and then you jump to a location based on the setting of mtvec. So mtvec is the machine trap vector base. This is another CSR. So the way mtvec is set up, there is a 2-bit mode field at the bottom to determine what mode of vectoring you have supported. And currently, we've defined 2 modes, direct and vectored. And those 2 bits, any other encoding is reserved for now. But you put the aligned address of the trap vector into the other parts, the upper bits of the base register. So the 2 modes are direct, where every exception and interrupt will go to that one address. So everything goes to a single location. So the processor just jumps there when it gets an interrupt. In the vectored mode, all the synchronous exceptions do the same thing. They go to that one address at the base, but all the asynchronous interrupts, those get vectored depending on which interrupt it was. So that then spreads them out and separates the different interrupts, so you can have custom handlers there. So just to go over that again, so if you look at the mcause values, the exception codes, these are all the different interrupt numbers, and the base of this number is just the bit position in the MIP register. And so if you add more custom local interrupts, those would just be additional numbers down here, sort of 16 and up. We've reserved 12 to 15 for new interrupt schemes. Right, so then when you take an interrupt, the machine will just jump to base vector plus cause times 4 bytes. So you have 4 bytes per interrupt, and the machine just jumps there. And when you jump there, interrupts will be disabled on entry to that handler. So there's a few things that go on when you take an interrupt. You record the interrupt ID in cause. You remember the place you came from in EPC. You push the privilege stack. You disable interrupts. And then you jump to a handler and start executing there. So just to kind of highlight this, there's sort of 2 parts from interrupt. There is what you were doing when you're interrupted, which is the save context. Then there is what you're going to do to handle the interrupt, which is where you're going, like where you came from and where you're going to. 2 pieces of doing an interrupt. So where you came from is this interrupted context, and that's saved as another register. MEPC holds in this case, the machine mode exception PC, holds the PC of the interrupted instruction, and then you'll stack the previous interrupt enable and the previous privilege mode in these 2 fields in the mstatus. These fields are important not just to save it on when you take the interrupt, but when you're returning from the handler, the mret instruction, mreturn will take this EPC value and put it into the PC, and pop the stack and put the privilege mode and interrupt enables back into the current privilege mode and interrupt enables. Okay, so this is how you restore the context. So that's kind of a quick summary of the current interrupt scheme. It's pretty simple. We just kept it simple to start with. And now as people start using it and getting into it and realizing, well, it's not that sophisticated, there's a bunch of problems with this current interrupt scheme. So one thing is there's no preemption except via the privilege modes. So in the current design, every privilege mode has separate EPC and PP, previous privilege and previous interrupt enable fields. So if you're running a handler in supervisor mode, and so you have the supervisor EPC and the supervisor fields in the status holding the previous interrupt level and the previous mode and previous interrupt enable, you can then, while you're in the supervisor handler, take a machine mode interrupt and jump directly to machine mode handler, and once it's done, it'll return back and you'll be back inside the supervisor handler. So that preemption is possible, but only between privilege modes. So just between machine, supervisor, and if you have them, user mode interrupts. Okay. Those local interrupts, they do provide vectoring, but there's a fixed priority. So basically the bit order, plus a little tweak, that gives you effectively the ordering of those interrupts, the priority. So if multiple of them are pending at the same time, there's a fixed order in which you'll take the pending interrupts. But you do get fast vectoring in that case. You go straight to the appropriate vector. Now another issue is that we have this vector table, but it's something you jump to, and so it only holds jump instructions. So when you go to the table, you have to then jump again. You only have space to put a 4-byte jump instruction at each entry. And with the RISC-V ISA encoding, those jump instructions can only jump plus or minus 1 megabyte. Now, in a lot of cases, that might be okay, but sometimes you want to place the trap vector table in some RAM that's far away from the code where the handlers are. They may be in a different type of memory that's far away. Maybe the handlers are in flash, and the jump table's in RAM, or vice versa, or something. So it's inconvenient that you have to place the table that close to the code you jump to. And the other problem is if you want to jump further, you obviously can jump further in RISC-V, but to jump further, you need a spare register. And if you're an interrupt handler, you have to create an interrupt frame to save that register in order to use a register to create the longer jump offset. And so it gets quite clumsy. You end up using a lot of instructions, 4 or 5 instructions in total probably, to actually trampoline into an arbitrary jump address away from that vector table. Now the PLIC gives you the variable priority, so the different inputs you can reorder their priorities, but it doesn't have vectoring because it comes in as a single input to the local inputs. So you get a single cause, you go to a single location in the table, and then you have to go to the PLIC, read out which interrupt it was, and then do the vectoring in software to go to the right interrupt handler. And so this, to claim the interrupt, you do one memory access at the start of the interrupt routine to go to the PLIC and claim the interrupt and find out which one it was. And then once you're done, you need a second access to tell the PLIC that you're finished with that interrupt to complete. So that's an additional 2 memory accesses you need to do in the handler. And the thing about the memory access is it's not just the memory access. You have to make sure you have the address that you're going to created. So that might require another instruction or 2 unless you've set up a scheme with registers holding that address, right? Now another problem we have is that the Unix ABI, which is the only one we standardized, which is the thing the Linux distributions are based on, it's designed for high performance running code. It's not designed for quick context switching. The model is you want to run code most of the time, and in Unix systems you don't get interrupted that often comparatively. And so the ABI is optimized for performance on running code, running tasks. But in terms of interrupts, there's a lot of registers you have to save restore to handle the interrupts. So Unix ABI requires a lot of registers. So 30 seconds? No, clock's wrong. Right. So everybody realized these issues. So we had a bunch of people, providing input to improving this. So this is still early days. So we're still at the point of gathering ideas, trying to factor out the components, come to agreement on solutions. We'll just go over some of the points people brought up. So Andy's at the last workshop presented an enhanced PLIC design. And what this does is, based on the PLIC, adds stacked preemptive vectoring to the PLIC design. So you will immediately, the core can, with the right configuration, the core will take the interrupt directly instead of having to claim. It will automatically stack the priorities of the preempting interrupts. And this is basically in addition to the existing PLIC. So Syntacore had a proposal where they tried to, it's interesting, so Andy's tried to enhance the PLIC. Syntacore wanted to enhance the local interrupts by restructuring them. So you have this fast local vectoring, and with reusing the delegation to give you preemption via there. So Seagate, that's not right. I think, okay, wanted to add vectoring on top of the PLIC. So Liviu, individual member, he's been pushing for more interrupt levels, doing more of the stacking in hardware, so having hardware stack to save and restore the registers, and also a new embedded API to reduce the amount of context we have to save and restore when we take interrupts. So on the Sci-Fi side, we've been working on this as well. We're kind of keen to have a scheme that's going to work across a bunch of privilege modes and also on higher performance cores. And so we've been emphasizing accelerating a software solution. It's easier to put that into a higher performance core than something with hardware stacking. But anyway, these are all the inputs. We're still discussing and working through this. It's still early days. But to give you some idea of the components of these ideas, how they go together. So one other thing is an important aspect here is the software interface to interrupts. And some discussions on the list, we figured out there's basically two models that we think are interesting. I'll describe those as a regular C function and then an inline handler. So the regular C function model is that your interrupt service routine is a regular C function. You compile it, the regular C compiler, and you just put that in the function address table, and the machine will just jump to that function and start executing a C function as your handler. The other option is an inline handler, where it's a non-standard C interface. It looks like you can write C code, but you have to compile it with a different convention on saving and restoring registers. Basically, you save registers as you go. Now, in my opinion, this is my opinion, I'm not sure everybody agrees with this, but I think both are needed. And the reason is C provides this convenient interface, but if you mandate that everything has to have a C interface, you're mandating that you have to save and restore a bunch of registers around the ABI, even on a short handler that may not need to do anything with that. So it becomes kind of a heavyweight, regardless of what you do, right? So you can mandate one model, but it's always going to be intrinsically heavyweight, whether you do it in hardware or software, to save and restore that context. So to give you an example of the inline interrupt, for those of you who haven't seen this, this is a standard thing already supported in GCC for other architectures. So it's not something new for RISC-V, it's just turning this on for RISC-V, really. So this requires no changes in the ISA or anything, it's just a compiler flag. So you'll just say, attribute interrupt on a function. This is an example little handler. So what this little handler does is, all it does is when it gets an interrupt, increments a counter in memory, right? That's the sole function of this interrupt handler. You can view this as, say, a little microcontroller. It had some number of timer counters, but I had like 20 pins. I wanted to count 20 events on 20 pins, right? So I want to just do a little simple bit of code that just increments a counter. So you can write this in C. There's a little bit of if-def here, just in case you do or do not have the atomic extension and how you do the fetch and add. But once you compile this to GCC, you get something like this. And so this is the entirety of the interrupt handler, including all the save restore. So basically, in this model, you'd have every register is call save. So you save as you go inside the interrupt handler. It's inlined, okay? So the handler, you see the first thing it does is create a frame. The other assumption in interrupt routines is you're going to use the stack of your current mode, and you're just going to add on to that. And the convention is you have to push the stack before you save anything. Only positive offsets from the stack are guaranteed not to be trashed. So you first claim a frame by bumping the stack pointer. You then, in this case, you save a couple of registers, save a register, clear the interrupt flag just by writing 0 to it, save another register, load the address of the counter, load a 1 immediate, increment the counter, restore the registers, restore the stack pointer, and return. So if you vector straight to here, you can, just those few instructions, you'll have done the interrupt and returns, right? So that's pretty quick, and if you're doing something simple, it's very low overhead. Now, if you want to actually jump to a C function, With the current Unix ABI, there's a lot of registers to save and restore. So this is kind of a sketch of what you have to do. You're bracketed by creating a frame, but then, I sort of wrote this in shorthand, you have return address register, 7 temporaries, and 8 arguments to save, and then you can jump to the handler, and then on the way back you have to restore these. So you add 36 instructions to do the save restore for each interrupt handler, which is a lot of code. And if you want a vector as well, you're going to multiply that by the vector points. And generally, you don't want a vector if you're going to be doing software save restore, right? And this doesn't include the floating point context in case you have to save and restore that. So now, one thing to notice is you can put all this in hardware, but it's not going to, intrinsically, if you have to save that much stuff to memory, it's going to take you that many memory cycles to do it. So this is why we're sort of thinking about we really need to work on an embedded ABI as well. That's different than the Unix ABI, maybe emphasizing or balancing context save restore with straight line performance, right? So some of the options in vectoring. So I'm sort of going through the different components of the interrupt scheme, people are proposing, looking at the options there. So I mentioned how the current PC scheme, PC jump constrains the range. So a lot of people like the idea of, well, you just have the vector table instead of holding a jump instruction, should hold the address that you should jump to. So that's a very simple model, very simple for the user to use. The thing, though, it does, it means the hardware has to go fetch that pointer and jump to it atomically, which is not a natural thing. It's a new thing you'd have to add into a pipeline. Simple pipelines, no problem. More complex pipelines is kind of awkward to add this. There's nothing else kind of does something like this in the pipeline. It's a little unwieldy to add. It's possible, but it's unwieldy. So on proposal on the sci-fi side, we've been looking at doing something that looks funky at first glance, but we like it because it simplifies the pipeline. It's almost the same as putting the function address in the table. It's just the low bits you set to this pattern. And then when you take an interrupt, you switch your ISA to a new ISA that has a jump relative by this amount. And that means your processor pipeline thinks it's a jump. You flip a bit, it fetches that instruction, executes it as an instruction, which is a PC relative jump. And so it actually has the same effect as fetching an address from the table and starting execution there. But it does mean you don't have to change the pipeline. The pipeline just thinks it's an instruction fetch, albeit with a different encoding. And then the other thing about this instruction mode is it executes one instruction, then goes back to the regular instruction mode. The nice thing about this is you can actually preempt an interrupt at any point in this scheme, and things will work. So if you started doing this instruction and got a high-level interrupt, you could scrap that and restart the high-level interrupt. When you come back, you'll re-execute the instruction that would have taken you to the right place here. So this is the thing. It looks a little bit funky. It's almost the same as writing a function pointer. You just have to put these bits at the bottom, and you could also define that these could be 0, so these two schemes could be the same, almost the same. The user wouldn't be aware that they're putting an instruction there instead of putting an address there, right? Yeah, so another thinking about vectoring, if you're going to do software trampolines where you're going to do software scheme to save and restore and then jump somewhere, you don't really want vectoring because you're going to have all this code to the trampoline. You want to do that once and then have the software do the vectoring. But if you're doing the hardware vectoring, or if you're doing the inline the versions, you want to have the vectoring too, right? If you're customizing each handler to do exactly the minimal necessary to do some little bit banging thing, you want to vector those individually, right? So this is options there. So just going through some of the details. So now we add these new local interrupts, or these new interrupts. We'd like to be able to configure them, so each interrupt now, this is kind of saying how we handle delegation and other features. We'd like to have each interrupt now be configured with its privilege mode, like which mode is this interrupt going to be serviced at. And now we have this new thing, which is the interrupt level, which is the preemption levels. So in talking to various people, somewhere between 3 and 7 levels is about the most. Some systems like to have 256 nested preemptive levels. But I think a lot of people think if you're doing that, you really don't know what you're doing in your system if you have 256 levels of preemption. So this is a thing to figure out, is how many interrupt levels we really need to support. And then finally, our priority, which is just within a level, and there are multiple pending. You don't preempt, but you will service the pending ones in that priority order. And there's various schemes to, if you have a fixed number of bits in the interrupt controller, how you allocate those between mode, level, and priority. within the interrupt controller. And if you do this well, you just need a single circuit that does basically a max reduction to give you the highest one of these to service next in the core, right? And you can figure out if this highest one means you should preempt or not, based on privilege and level. So another thing is you have to manage, when you take the interrupt, you have to manage the context state. And one reason we disable interrupts is we only have one copy of EPC and cores in the hardware. So you need to at least save those before you can enable interrupts to allow yourself to be preempted. So again, managing this state, you can push and pop these values onto the stack using either hardware or software. We have this new thing. You have to remember your previous interrupt level as well. So at any time now, the core is running in some mode with some interrupt level and with interrupts either enabled or disabled. You have to remember that context and restore it when you do the mret. And so when you add more levels, we used to have this stack in mstatus, which was the MPP, MPIE, but that's only for one level. You had regular execution and interrupt. Those were the only two levels we had in the original scheme. Now you want to nest and have multiple levels. You have to remember the previous privilege of each of those. The model now we're looking at is putting those into cores. So cores will record this extra field, these extra fields, and this makes it quicker to save and restore that context, the interrupted context, when you have more levels, right? So this will then replace the MPPM PIE stack in mstatus. All right. Okay, so there's a bunch of other issues. One is handling multiple privilege levels, security, and stacks. So one thing I didn't get in time to look at was you may have multiple privilege levels. You take an interrupt from, say, supervisor mode into machine mode. You want to use the machine mode stack and not the supervisor stack. But if you're in that machine mode and you get a second interrupted machine mode, you want to use the machine mode stack. So you have to conditionally swap the stack pointers based on which mode you came from, which mode you're in. Another thing we want to look at is quickly servicing remaining interrupts. Once you've done one interrupt handler and have taken the time to save the context, if you have another interrupt pending, you want to just go take that interrupt directly without first restoring the context and then saving it again, and then jumping to the handler, right? So it's called tail chaining. Another thing is the interaction of this with virtualization and large numbers of MSI interrupts. So I think I'd like to be able to use this scheme to also handle message signal interrupts, large numbers of them for things like PCIe devices directed at individual cores, but this is something else we have to work on. So this is all work in progress. We have a task group meeting on Thursday, 3:30 to 4:30 for the members, so please come if you're interested in helping out with this task group. So that's it. We're out of time.
Yeah, quick question. Obviously, correctly handling interrupts, no matter what the scheme, is very tricky and easily can go wrong. It might be good for the task group to also publish sort of canonical implementations of interrupts for people to use. Does that make sense?
Sorry, say again.
For the task group to sort of publish canonical implementations of interrupt handling for people to use so they don't screw it up.
Okay, so software examples of using it. Yes, okay. Yep. Yep.
So I know in x86 architecture there's a concept of ordering, event ordering when an interrupt is handled, when it's serviced, when you tell the interrupt controller, go ahead and send me the next one. Has that been built in here? Because the software expects a certain machine state to be persistent when it tells the interrupt controller it's done.
Right, so in the PLIC has the notion of you claim an interrupt, so software claims it, and then at some point it says I'm done and completes it. And that lets the hardware know it's okay to have a second interrupt for the same device be taken. In the fast interrupt schemes, I think the model is for the level-sensitive interrupts, which is going to be supported. You'll expect the handler to clear down the thing and make sure it's done. If you have edge-triggered interrupts like the MSIs, when you take it, it's going to clear it down and know it's gone. So you don't have to explicitly go back and tell it it can take another one. If it's at the same priority, if you have one bit, and so clearing that bit down when you launch the handler will tell the device in turn that that is now being cleared and accepted, another one can show up. Yeah. That's the model.
Sorry, why not just for each like vector entry you have 4 instructions so that you can jump to arbitrary location? Why you just have 1 instruction and then you have limited jump range?
Okay, so the question is, if you only have why only 1 instruction in the jump tables? That was to save the size of the tables, and sometimes you want to jump to a bunch of things will jump to the same handler to do the same thing. We could have had 4 or expanded that out, but then you would need more code to do that, and it'd be the same code at each place. And the real problem with the extended range is you need the spare register. So you need enough code to save a register in which you can build the longer jump offset. So that's like it becomes more than a couple of instructions. You have to save the stack pointer, you have to increment the stack pointer, you have to dump out save the register, you have to do a AUI PC, and then you can do a jump and link. So it's 4 instructions. But it also adds, you still have to do the stack pointer update in the thing you jump to as well, because this is just your local stack pointer update. So we could increase it to 4, and that would increase the range, but then you still have these 4 cycles of getting, you jumped here and you create 4 cycles and jump again. People feel that's a lot of overhead. So.